Okay. You had to evaluate these algebraically. Now, yesterday also, I put this in your graph. So, do you think it's a good thing to pick up your graph and go to your y equals and put this in there and see what it looks like? Yes. So now, direct substitution. I laid them out for you. We take a look at this. There is no domain restriction in this parabola. This parabola in your y equals opens down. There is no domain restriction. So any x that we plug in, we directly substitute it in here, and we can evaluate this. Substitute, evaluate. And that is the limit of this equation. It is the y value of your function. So we say f at x, the x is at 5, and we look at the value. The limit. The y value is your limit. It's the value of your function at that point of x. So what happens is, well, this one is a direct substitution. So we're able to say it's direct. You put it in, and that gives you your y value. Sometimes we can't. We have to, cancellation and do everything. So we look at as it approaches. This is as it approaches 5, but we can substitute 5 directly in here. This guy too, if you look at this denominator, if you set this equal to 0, this is not real. So therefore, you have no domain restrictions. There's not one x that you can't use in there. If you used a 0, you'd get 1 in the denominator. If you used a negative or positive, it's going to square it to be positive. There are no domain restrictions here. So as it approaches -3, we can directly substitute this in. We have a value for y when x is -3. So we substitute this in, and we evaluate the function. As x approaches -3, we put the -3 in here, and we evaluate your function. So your y value for this would be -3/5, -0.6, if you did this. If you put this in your calculator, it's even easier because you can go to your table. You can see there's a value there when x is -3. I wanted you to solve algebraically, yes, but confirm it in your calculator. This is ln e. Well, what happens to your ln e? Your property says ln e cancels itself out. The natural log and the inverse natural log, it cancels out. So it's just whatever the x is. So again, our restriction is just in our domain, but we can use our -3 here. So therefore, you just set it equal to your x, -3, and graph that. You can put that in your y equals. Just to show you there are other things you can put in here. Here's a sign. You can put this in here. Now, this is also a direct substitution. Is there any restriction for that denominator? No. So I take the 1 and I put it in for my theta, my angle. Your angle has to be in radians. If you graph this, your mode has to be radians, and you have to do a zoom trig on this. Easier to do by hand. If you put a 1 in here, this is 2 pi over 3. So, if you remember, this is 3 pi over 3. 2 pi over 3 is right there. 3 goes into 180 60 times. There's your special right triangle. And the sign is the y over the x. The y over the r. And there's your y over your r. That's all you wanted for that. Okay? If you did it in your calculator, you would probably see the 0.866 because it doesn't give you a radical, it gives you, the decimal of it. But you have to find this algebraically. Algebraically, this is a good way to do it. Well, that's because you didn't solve it algebraically. You solved it with your graph.
I solved it algebraically, but then I just put the sign into the...
Oh, you put it into your calculator. Yeah, if you noticed it was your special right triangle. I mean, it's not wrong, you knew what you were doing, but you should have been able to spot your special right triangle and used it from there. Okay, now we get into your cancellation part, which means that we generally have some kind of restriction. So we have to get rid of this so that we can use this. You're using one function here, which is this, and you're taking a limit as it approaches different numbers. Here's your function that you're using. Easiest thing is also put this in your y equals. You're going to be able to tell a lot by looking at your graph. And yes, you have to solve this algebraically, but you can kind of see where it's going with this. Now, we see your domain restriction right here. X cannot be equal to 0. So I cannot plug a 0 in here. I can plug in a -1. I can plug in a -2. That right here is a direct substitution. However, to do the 0, I'm going to have to reduce it anyway. So we're going to factor and reduce. The function, the factor that we take out, that we cancel out, is your point of discontinuity. So therefore, when x is equal to 0, this one, that is your point that technically does not exist. It looks like it does on your graph because your graph has nowhere to jump over that little tiny point. But on your graph, that's where you put your little open circle. That's your point of discontinuity. Today we're going to talk more about a removable and a non-removable point. If you can look and see where it approaches from both sides, then we can fill it in. We can remove that point of discontinuity. So once we factor this is your reduced function. You can plug all of these pieces into this reduced function, and you will find the limit of the equation as it approaches 0. Your y value will be 1. It doesn't exist for your 0, but it's a little point that if we could reach it from both sides and it reached the same point, that would be where its limit is. And the other ones you can just plug in, because there is a value at -1, there is a value at -2. The nice part about graphing this is you can see it right away in your table. 0 will say error, -1 will give you a 3, -2 will give you a 5. Because your only restriction is the 0. Were you guys able to see that from this? I think this is a nice one. I believe too, if you graph these things, it just makes such a big difference. Now your domain restriction is in your denominator. So x cannot be 1, because that would make this function undefined. We want to see, as x approaches 1, what value of y would be there. So the very first day, again, we graphed it. We looked at the point where it converged at the y. Then we did it algebraically. So in order to get rid of that denominator, we factored and reduced. That's what tells me try factoring and reducing it. I can't plug my 1 into there because it's not going to work. So if I can get rid of that denominator, I should be able to plug my x of 1 in there. So we factor, and then there's your perfect squares. This guy comes out. This is your point of discontinuity. That's this guy. Technically, that point doesn't exist. It's a little open circle. But if I look at my limit as x approaches 1, it would converge where the y is equal to 2. This one you were able to do, and this one you were able to do. And since you've already shortened it, you might as well just plug it into your reduced function. And confirm it on your calculator. It makes such a big difference. Well, these two would work because they didn't have a domain restriction. But the first one has a domain restriction, so we had to factor and cancel it. Cancel out your factor. Remember back, like a few months ago, whenever we took that factor out, that was your point of discontinuity. That was the one point that looked like it was filled in, but was not. And whatever was left in the denominator, if you remember back, if we didn't cancel it out, happened to be an asymptote, which made one of those lines which made your end behaviors kind of go off. This is kind of a good time to do limits because it does force us to go back and review what we did. Okay, this one again, as you approach 7, you cannot put 7 into that denominator. You would get undefined. So therefore, we reduce it, we factored and reduced it, and we took your reduced function and we plugged the 7 into this x. And we've got your value. Now, I confirmed it on my calculator. As I approach 7, my calculator says error. But it came from the left and from the right. It converged at that y point, which is your limit for that value. Okay?
Get that chart, you just put it in the y equals.
You put this in your y equals, watch your parentheses, and when you realize where your error is at the 7, because you can't put a 7 in there, it'll come down and say 7 error. Because that's the one that when we factor this out, this side's going to give you an asymptote. The negative 7 is also going to tell you error, but the negative 7 will actually have an asymptote here. That forces your edges to go off. But at the 7, wherever it goes, you won't be able to tell that that's an open point. You won't be able to see it. It will show in your table. So once we factor and reduce it, we can plug your 7 in. On your table, just narrow down to this guy and then start it at 7 and increment by 0.001. If you see it converge from both sides to the same point, so these are basically the same, right? So then we know our limit is going to be 0.071. It's going to converge at that point. If I could just fill that in, it would be that point. And if you remember back to when we found your point of discontinuity, we replaced it into your condensed version there, your factored form. And that's how we found your y value. Okay, the next one, notice your domain restriction is -1. So we have to factor and reduce. This is a good factoring thing for you guys because besides fractions, you hate factoring. So this one is just the opposite factor. Normally you see your 3x squared in front, and you take your factors of 3, 1 and 3. This time, take your factors of 1, 1 and 1. And then take your factors of 3, 3 and 1. Just put the x right next to that. Then, play with your plus and your minus signs. If you need a negative here, and you need your larger number to be negative, the negative has to be right here by the larger number. And then there's your positive. And try it. Boil it back out and make sure that it becomes that. Generally, if you take your factors of your first term and your last term, they work. You just always have to test your middle terms. So we factored and reduced. The factor that we were able to cancel out is your point of discontinuity. That's the point that you're looking for. Again, I just confirmed it on my calculator that I would basically be coming to 4. My y would be approaching a value of 4 as I approach the value of -1 for my x. And algebraically, just take your reduced format and plug in your -1. Oops. I don't know what happened here. Oh. Honestly, don't know what happened to my board. Okay. This was rationalized. Remember we said your domain restriction now is in your denominator. You can't have a y of 0. So therefore, you want to eliminate that y. You can't square it, you can't radical it because it still has a 0 factor in there. So you take the conjugate of the numerator. You multiply top and bottom by its conjugate. This is the same thing if I said rationalize this thing right here. You multiply top and bottom by radical 3. So you have to multiply numerator and denominator by the same conjugate. Conjugates are perfect squares. So you multiply the first term, then you multiply the last term. Then you combine your like terms, the 3's will cancel out, negative and positive, and you're left with a y. And you're just left with a y for now. Bring this over, so now you got the y times this, don't distribute it. Now your y's will cancel out, and you're left with a 1 on top. And that's okay to have that mess in the bottom, because now you can substitute in your 0. That was your goal, to be able to substitute in your 0. So when you rationalize this, you have to rationalize your numerators. Okay? And again, confirm this on your calculator. Now confirm that it works. Because that looks like a really small point, but in fact, it's fine. Bless you. This guy too, this was a little bit trickier. Keep this hook together. Hook this guy together. Keep it together. You multiply your tops. There's your x plus 7. There's your negative 4. Combine this. You get x plus 3. Slide this over. Here's your x plus 3. It comes out. So you're left with 1 over that mess. And that's okay to leave that in your denominator. It just allows you to enter a negative 3 in there. The rationalized look worse than they actually are. Because when you get to your denominator, your numerator is perfect squares. First term, last term. Your denominator, slide it over. And see how that works. Don't distribute anything. Don't FOIL anything. Just slide it. If you can't cancel that out, something happens. Chris? Do you see it? Numerator? Denominator. Numerator? It always pops out of your radical. And I always start like this. Negative times a positive, negative. I put my negative sign first, so I don't forget it. And then combine your like terms. Combine your like terms. Yeah. Okay. And what else we have? Oh, complex fraction. Complex fraction, you can do it any way you like. I did it combining the top and then the bottom, but personally, I like to do it all at once. Find a common denominator. Make everybody have a denominator. Now, look at the factors that you need. Look at all your denominators. What's the factor you need? X plus 1. Just pull out which denominator you need. I need that, and I need a 1. So my common denominator is x plus 1. Put it on the top of every term. You have to multiply every term by x plus 1. Out comes this guy. You're left with a 1. Well, 1 minus that, just make sure you keep your parentheses, x plus 1. And this guy, x times x plus 1. Don't distribute anything. You cannot cross out your x plus 1s because these have 2 terms. Instead, distribute your negative sign. Now, combining your like terms, you can cross out your 1s. So I'm left with negative x over x times x plus 1. These are factors. So now you can take out an x, and what's left in your numerator? A negative 1. Okay? So you're left with negative 1 over x plus 1. Now you can put in your 0 in here. Negative 1 over 0 plus 1 is 1, equal to negative 1. So the limit of this function as x approaches 0, it doesn't exist. Well, it's not there, but it's not a number we can see. It's a point of discontinuity here. We can fill it in with a value of negative 1 for your y. And again, confirm it graphically. Putting this in your calculator is a little tough. You need parentheses here, you need parentheses here. If you use your fraction key, it's probably the easiest to use. You need two sets, I guess, of fraction keys. This one again, there's your 0 in your denominator. You want to get rid of this x. So rationalize your numerator, reduce it, and then you can plug your 0 in. You can find your limit. How were these? Yeah? Did you see where you made your mistakes, or you just decided not to do them because they look so bad? I think most of you decided not to do them because they look so bad. They're really not bad. Again?
What was the other one?
Sorry?
For number 12. Oh, 25.
Negative 1/2? Negative 0.5? Okay. This one, complex fraction again. Put this over 1. I would find my common denominator. What is your common denominator? What's your common denominator? What factors do you need? I need a 3. And what other factor do I need? 3 plus x. Easiest way to do it is like this. Out comes the 3 plus x. I'm left with a 3. Out comes the 3. Be careful of your negative sign. This I need to multiply. 3x, 3 plus x. You cannot cross off through 3 plus x. These are two terms. Distribute. 3 minus 3 minus x. Out comes your 3's. Out comes your x. So negative 1 over 3 times 3 plus x. And you can leave it like that. Don't distribute. You can just leave it like that. In fact. Now you can plug in your x of 0. Again, look at it on your calculator. You can tell right away if you're wrong. You can confirm it on your calculator. Good? This is a tougher section. Are you good with this or no? This part here, again, algebraically, we can't solve that with the 3 in the denominator. That's where your restriction is. So it's easier to solve this one using your graph. From the left and from the right, if you notice this 3 plus, this comes from the right. From the right as it approaches 3, from the left as it approaches 3. And they converge at different points. They don't converge, actually. This one approaches 1. This one approaches negative 1. We use a plus sign to say from the right because it's coming from the positives. We use a minus sign to say from the left as it comes from the negatives. The negatives approach negative 1. The positives approach positive 1. They don't have a point in between. The limit does not exist. If you graphed it, you'd see this. All right. And this is your last one. This is a piecewise. Again, all you care about is this point right here. You plug the 2 into here, and you get a 1. And you plug the 2 into here, and you also get a 1. So from the right and from the left, they both approach 1. So one is open, one is closed. Okay, so that you can figure out that y value, which is 1. If they don't converge at the same point, then there's no limit. The limit doesn't exist.